I guess what we're going to be looking at here is we're going to be going over Taylor series, the vocabulary that goes with it, things that you might see on the AP test, and examples of quite a few of the different types of problems. So this video is a little bit longer, so just be prepared for that. But at the same time, hopefully everything that we talk about in this video makes sense, and you can see what we're doing through the examples that we have. So let's just go ahead and get started. So when we talk about a Taylor series, or just any type of power series in general, remember that a Taylor series is just an infinite series that is a polynomial. In other words, just like we talked about previously, it's something that goes on forever, that you see a pattern that it follows, and these have x values in them, okay? And we'll talk more about how to build a Taylor series a little bit later, okay? One of the things that's true about a series is you can manipulate a series in a lot of different ways to create a new series. So if I know, like, the Taylor series for e to the x, I can find the Taylor series for e to the 2x or e to the x squared, and it's very easy to do. I just substitute in. Or if I need to take the derivative or the antiderivative of something, same thing. I can just take the derivative or the antiderivative of that series. The difference between a Taylor polynomial and a Taylor series is that a Taylor series goes on forever and ever and ever. You just have one term after another following this pattern we're talking about. A Taylor polynomial ends after a set amount of terms, okay? And honestly, on the AP test, this is more just specific to the AP test. If you don't know what you're doing on a problem, like you're like, I have no idea what to do, at the worst, you could try using the ratio test, and we can talk about that later, okay? So the first type of problem I want to look at is write the first blank non-zero terms of Maclaurin or a Taylor series, okay? What this is generally telling us to do is it's saying, okay, I just want you to write the first couple terms of a particular Taylor series. Sometimes you'll have to construct it using this formula right here, and that dot shouldn't be there, so don't worry about that. But where we take whatever term we're on, we take that derivative and plug in where the series is centered, then we have x minus where the series is centered to that same number power divided by that number factorial. So if I had like the fourth term and it was centered at 0, I would take the fourth derivative of the function we're trying to mimic and plug in 0, then I'd have x minus 0 to the fourth power over 4 factorial. So here's an example of a problem where we would have to do this. We've got the Maclaurin series for e to the x, and then it actually tells us what the power series is to start here. Then it says write the first 4 non-zero terms. We'll get to the general term in just a second, but write the first 4 non-zero terms for e to the x minus 1 squared about x equals 1. Well, on this one, what we have to realize is I have e to the x right there with the arrow pointing to it, and I want e to the x minus 1 squared. Now, what we have to realize in this problem is I'm replacing x with x minus 1 squared. It's not that I'm shifting or squaring. I'm just replacing x with x minus 1 squared. If that's the case, then I just have to replace x with x minus 1 squared everywhere that I see it. So I get x minus 1 squared plus x minus 1 squared squared. So that'd be like to the fourth power divided by 2 plus x minus 1 squared to the third, which would be to the 6th divided by 6. And there are the first 4 non-zero terms in that particular series. Now, hopefully you can see, again, all I did, and everything when you do these problems, you always just replace the x with that's what changed. Now, when we write the general term of the Maclaurin series or the Taylor series, we just have to recognize usually the pattern that is occurring first from the first whatever terms that we were looking at, okay? When we look at the general terms, and it's different on different problems. One we're going to look at here is actually pretty easy, but it's different on different terms. If you just have the first couple terms without seeing the general term, then you need to ask yourself, is -1 raised to the correct power if we're looking at an alternating series? Another thing you need to ask yourself is, are the constant terms written correctly? Do we need a factorial? Is the bottom, does it go 1, then 2, then 6, then 24? Do I see that pattern? Because that is a factorial if I see those numbers show up. Number 3, have we taken into account where the series is centered? Okay? And is the x being raised to the correct power for each term? Now on this one, the nice thing about this problem is it gives us the general term right there. Anytime you see x raised to the nth power with just n in it, that is your general term for the Maclaurin series. And sometimes it'll give it to you in a summation, sometimes it gives it to you in the infinite series. But all we had to do for our general term is take x minus 1 squared and put that in for x, just like we did in all of the first terms. Then I've got that right there. And honestly, I could leave my answer like that for my general term in this problem, or I could have x minus 1 to the 2n over n factorial. Oops, n factorial. Either one of those work. That's not always the case. It's not always that easy to find the general term. Sometimes you really have to do some analysis. So we'll do some examples in class later that hopefully those make a little bit more sense. The next thing we're going to talk about is how to find your radius of convergence. When we create a Taylor series, we can't just plug any x that we want into any Taylor series. Some of them you can, and it'll mimic the function the same way when we try and evaluate it, but not all of them. Some of them have certain x values that you have to be able to plug in, and then once you get away from that, you can no longer plug those into your Taylor series because it won't give you the same values as the function that you're trying to mimic. Long story short, what we do here is we use the ratio test. We use the ratio test, and we say, okay, I'm going to use the ratio test here, but I want my ratio to be less than 1, and then we solve for x. As we work through the problem, we'll get to a point where we get x, and it might be minus a number, it might not be minus a number, but basically we have the absolute value around something, and it's going to be less than a number. That number that it's less than is what is known as our radius of convergence. And honestly, it just comes as we're doing this problem. So here's one right here, okay? So I've got the Maclaurin series, the function f is given by, and then we've got, again, this is our general term right there, and we want to know our radius of convergence. Well, the way that we do that is we take the limit as n approaches infinity, we take our general term, and we put that on the bottom of a fraction. Okay, so I got n minus 1. Then on the top of the fraction, we do the exact same thing, but we add 1 to everything. So n plus 1, I've got 2x to the n plus 1 over n plus 1 minus 1, which is just n. And I want to know what x values of that are going to make that less than 1. Well, in order to do this, we've got to take our fraction on the bottom and multiply the reciprocal of that, to the top, and then see what is going to cancel out. So I've got all of this stuff right here. I've got n minus 1 on the top. So I can see that there'll be 1 negative 1 left on the top and 1 2x left on the top as well. Okay, and we still have absolute value around those. Remember, this is the limit as n approaches infinity. So what I really look at there, and this is, I'm going to put this off to the side, although you don't have to do this on the test. I've got the limit as n approaches infinity of n minus 1 over n. Well, I can see that they're raised to the same power, so this thing is 1. It's not that the n's cancel out here. It's just as I take the limit as n approaches infinity, those two, because we're looking at such large values, the minus 1 doesn't matter, then they cancel out. So what I really have here is negative 1 times 2x is less than 1. Well, in order to finish this problem off, first of all, the negative 1's not going to matter because absolute value is that part you're like, okay, I don't need to worry about it because that just makes the value positive. But I need to get the x by itself here to find my radius of convergence. Okay, I can still have something adding or subtracting, but I can't have a number multiplying x. So I get the absolute value of x is less than 1/2. That right there is our radius of convergence. That's what we know. The absolute value of x has to be less than 1/2. That means the furthest we can go from where the series is centered is 1/2 in either direction. Okay, so once we find our radius of convergence, usually what we use that to find is our interval of convergence for that same series. So instead of stopping at the place where we just stopped right there, we separate our inequality into two separate ones and then solve for x. And we're going to do that, so we might as well, remember we had the absolute value of x is less than 1/2. So what that means is I say that x has to be less than 1/2 and at the same time has to be greater than negative 1/2. Now the thing is, we're coming back there in just a second, the thing that makes this more difficult is the x values that we're looking at, or excuse me, on the end points, if I were to plug those into my series and try and use the ratio test, I would get inconclusive. What we have to do once we get to this point to find our interval of convergence is see what type of series is built at both of those points by plugging that number in for x. So if I take negative 1/2 and I plug it into this series, so I've got negative 1 to the nth multiplied by 2 times negative 1/2 is negative 1. So I've got negative 1 to the nth power again over n minus 1. Well, if I have two negative ones every single time in the problem, those are always going to give me a positive value. So I've got 1 over n minus 1. This is the hard part right here because you have to be able to look at that and say, oh, you know what? That is a harmonic series. Because that is a harmonic series, that means that this is going to be a divergent series because I've got because it's harmonic. And again, hopefully that makes sense. So what I would say is negative 1/2, I am not going to include that endpoint. Then I have to do the same thing at positive 1/2. Okay, so I go and I make my summation n equals 2 to infinity. And I have negative 1 to the nth over 2 times 1/2, which is 1 to the nth power. Well, this time, since it's positive 1, that 1 raised to any power is just going to go away. This is negative 1 to the nth over n minus 1. That is an alternating harmonic series. So when I see an alternating harmonic, that changes things a little bit because I know that an alternating harmonic series is convergence. So what that means is I would include that endpoint. And this is the type of work that you would have to show on the AP test. You just have to say, okay, I recognize that as harmonic. I recognize that's alternating harmonic. Basically, when you get to this last step, you have to say, okay, this is what test I would use to show that this is convergent, or this is why I know that it is divergent at that point. So my answer on this one would be right there. Again, a little difficult, but not awful, okay? The next one, I'm not going to show an example for this because I couldn't find a good one that I could fit onto the notes, to be honest. But if we have to show that a Taylor polynomial approximation differs by less than a particular number, if we have an alternating series, so if we have a Taylor polynomial, I'll just make one up. Let's say we'll just go with e to the x, okay? So I have e to the negative x, excuse me. If I had e to the negative x, I would have 1 minus x plus x squared over 2 minus x to the third over 3. If I wanted to know how far off that Taylor polynomial was, if I was to plug in, let's say I was to plug in 0.2. So I want to know how close, if I plug in 0.2 for all of these x's, how close that would be to the actual value of e to the negative 2. At most, that would be off by 0.2, excuse me, not negative 0.2, times x to the fourth over, oops, this is over 6, not 3 factorial, or 3. So the next unused term, notice I finished at the third term, okay, or the fourth term, the third power. At most, my series is going to be off by, oops, and this would be negative 0.2, not that it matters. At most, it would be off by that amount. In other words, anytime we look at a Taylor polynomial approximation, you'll usually be asked how much is it off by. And if you're looking at an alternating series, you just say, oh, what is the next unused term in that series? Plug the x value in, and that is at most how much you will be off by in that alternating series. Now, what will happen sometimes is they'll say, okay, write the first couple terms and the general term of the derivative. So it'll say, okay, here's your series. I'm giving you a series now. Write the first couple terms and then the general term for the derivative of that series. So let's say, again, I had this one right here. And I actually think it makes more sense just to look at it. So I've got my general term right there. And then it says, write the first 3 non-zero terms and the general term for the Maclaurin series of g prime of x. Well, the first 3 non-zero terms of the derivative, I could just take the derivative of each of those terms. So my first 3 non-zero terms would be 1/3, that's my first term, minus 3x squared over 5 plus 5x to the fourth over 7. We still take the derivative like we normally do with each of the terms. That part doesn't change. The general term on the derivative is actually pretty easy as well. And this is what that last slide was saying. When I look at the general term, what I have to realize is the -1 and the 2n plus 3 in every single term are just numbers. When you take a derivative, constant numbers don't change. The only thing that changes is the power. What we do is, okay, so in a general term, all these numbers are going to stay the same. So I still have 2n plus 3. But what I do is I say, you know what? I can take that power, because this is a polynomial, so it's always the power rule, and move that down in front. Okay, so I bring the power down. Then I take x and I raise it to that same power minus 1. Well, 2n minus 1 2n plus 1 minus 1 is just 2n. So this right here would be my general term. That's the key to finding the general term on the derivative, is you say, you know what, I just bring the power down, leave everything else alone, subtract 1 from the power, and that's my new general term. And they generally don't end up looking great, but there's nothing really here that can cancel, and that general term is correct. So hopefully, again, that one kind of made sense. The next one you might see is, right, the first few blank terms for a blank degree Taylor polynomial of a new function. Sometimes what you might see is you might know the Taylor polynomial for f of x, and they tell you to multiply that by x. Or maybe it might say e to the x times f of x. What you do then is you just write down the first couple terms from each of those different functions if they have one, or on this one, like x times f of x, all we would do on this one is we'd say, okay, we've got f of x, I know what that is, just multiply x into everything. For e to the x, we would just write out my Taylor series, so I'd have 1 plus x squared over 2 plus x to the third over 6. And then I would say, okay, I'm going to multiply that by whatever f of x is. Then we would just FOIL in one at a time until we get to the desired power, okay? Now this one's a little bit different. This one says let f of x equals the ln of 1 plus x to the third. And we've got it, they give us the Maclaurin series for 1 over x. They want us to write the first 4 non-zero terms and the general term for the Maclaurin series for f. We'll notice in this problem, just like the first example we looked at, that the only difference between ln of 1 plus x and the ln of 1 plus x to the third is x has been replaced with x to the third. So that's all I have to do this problem, and I will get the correct answer. Okay, and I'm gonna show you one just other example of how we could do this here in just a second. So I'd have x to the 8th over 4 plus negative 1 to the n plus 1. That's a constant number multiplied by x to the third. And then that's n over n, like that. So that would be ln of 1 plus x to the third. But let's say I ask, what is x times the ln of 1 plus x? Well, I know that the ln of 1 plus x is this one right here. So I would just have x times each of those. X minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4. So I would just multiply the x in there, and I'd get x squared minus x to the third over 2 plus x to the fourth over 3 minus x to the fifth over 4. Then on my general term, I just gained an x in every single term. So really, when I think about this one, I would say plus negative 1 to the n plus 1 over x to the n plus 1 over n. That would be my general term. Again, hopefully that kind of makes sense. They don't very often ask you to make the general term. More often than not, it's a Taylor polynomial. So they might say, what are the first 4 non-zero terms? So I would just have to write those down for x times ln of x. Different problems, different times, just kind of matters on what you're looking at. All right, lastly, sometimes you'll be asked, okay, we have a Taylor polynomial. So it's not just like an alternating series. This time we have a Taylor polynomial, and we want to know, at most, if we use that Taylor polynomial to estimate what a function was, at most, how much is it going to be off by? Now, in reality, all we're doing here is the same thing that we did in an alternating series, in that we are using the next unused term in the Taylor polynomial. The only difference, so that's all what this is saying. This is just the next unused term. The only difference here is that when I go to find that, instead of plugging in where the series is centered into my derivative, I plug in the largest value possible that the derivative can give me. What that does is it ensures that my error is going to be at most off by that much, and it might be less than that, but I'm saying this is my worst case scenario. Now, when we do these problems like not on the AP test, that's actually a fairly difficult process to do. But on the AP test, just because they know that would take an awful lot of time, they almost always tell you how big that value is going to be, whether it's giving you a graph and saying, okay, how high is that graph? Or they might say the sixth derivative is at most this value. They'll always tell, they're not going to come right out and say you're going to use this, but that information will always be provided for you on the AP test. That is not something you're actually going to have to find. I don't have an example of one of these either, again, just because it wouldn't fit on the notes, but hopefully that kind of makes sense, and we will take a look at some of those problems in class. Hopefully all of those examples made sense, as well as those definitions, but if you have any questions, please please let me know.